Hey everyone. In the world of algorithms, we're always looking for ways to make things faster. But what if I told you there's an algorithm that doesn't just cut a problem in half, but shrinks it by its own square root? Today we're going to tackle a really fascinating recurrence relation. T of n equals t of the square root of n plus a constant. Let's dive in and see just how mind-blowingly fast this thing really is. So that's the central puzzle, right? Most of the time we're dealing with algorithms that chip away at a problem, like n-1, or they divide and conquer with something like n over 2. But shrinking the problem by its square root at every single step, that's a completely different animal. It's a massive speed up, and it needs its own unique strategy to solve. Let's just call this the square root puzzle. The very first thing we have to do is get the rules of the game straight and set up our recurrence relation. Just imagine an algorithm where each step makes the problem left to solve exponentially smaller. That's exactly what we're looking at here.
Okay, here's the formal definition. T of n equals t of n to the 1/2 power plus 1. Now, n to the 1/2 is just a mathy way of saying the square root of n. And that plus 1, we're just using it as a stand-in for any small, constant bit of work that happens at each step. The total time is just the time to solve that much smaller problem plus that one little unit of work. We also have a small rule. N has to be greater than 2. This is just a practical thing to make sure the problem keeps shrinking. If it got too small, the square root wouldn't really help us anymore.
All right, so how do we crack this thing? Well, our main tool is a technique called back substitution. I like to think of it as unfolding the recurrence. We're literally just going to keep plugging the formula back into itself over and over and just watch to see if a pattern starts to emerge. So let's get started. Here's our starting line, the original equation we're trying to solve. T of n equals t of n to the 1/2 plus 1. And now for the first expansion. The rule works for any input, right? So we can just take that t of n 1/2 term and replace it with the rule itself. What's the square root of n to the 1/2? It's n to the 1/4. So that gives us t of n to the 1/4 plus 1, and then we still have that original plus 1 hanging out at the end. Let's clean that up a bit. And wow, would you look at that? A pattern is already starting to show itself. The term inside is now n to the power of 1 over 2 squared, and the constants at the end add up to 2. See the connection? We're 2 steps in, and we've got a power of 2 in the exponent's denominator and a constant of 2. Interesting. Let's do it just one more time to be absolutely sure. And yep, it holds. After 3 steps, we have t of n to the power of 1 over 2 cubed, plus 3. The pattern is undeniable at this point. The number of steps we take seems to match the exponent on the 2, and it also matches the constant we add at the end. Okay, this is great. We definitely see a pattern, but we can't just sit here substituting all day. The next logical move is to generalize this into a single formula that'll work for any number of steps. Let's just call the number of steps k. And this is what that general formula looks like. After k times through this loop, our recurrence is t of n equals t of n to the power of 1 over 2 to the k plus k. This is the key. The number of steps k is showing up in 2 places. It's controlling the exponent, and it's also telling us how much total work we've done. This is awesome, but it leaves us with a giant question mark, doesn't it? We have this k variable just floating around. When does the recursion actually stop? And, more importantly, how can we figure out the value of k based on our original input, n?
And this, right here, brings us to the real aha moment of this whole thing. To solve for k, we have to make what I like to call a logarithmic leap. It's a clever little substitution that's going to unlock the entire problem.
Here are the 2 keys we need. First, we need a finish line. Let's just make an assumption that the recursion stops when the problem size inside the t function gets all the way down to 2. That's our base case. Second, to make the algebra a whole lot cleaner, we're going to change our variable. Any number n can be written as 2 to the power of something, right? So we'll just substitute n equals 2 to the m. This is a classic trick for making exponents much easier to handle. Let's walk through the math step by step. We start with our base case. The stuff inside the t function equals 2. Now, we bring in our variable change, replacing n with 2 to the m. Next, we just use a basic exponent rule to simplify the left side. We multiply the powers. So now we have 2 to the power of m over 2 to the k equals 2 to the 1. And this is the magic moment. Since we have the same base, 2, on both sides, we can just ignore it and set the exponents equal to each other. How cool is that? The problem just got way simpler. M equals 2 to the k. To get k all by itself, we do the opposite of an exponent, which is a logarithm. Taking the log base 2 of both sides gives us k equals log base 2 of m. We're almost home. We just need to sub m back out for n. If n equals 2 to the m, then m must equal log base 2 of n. We plug that in, and there it is, our incredible result. K equals log base 2 of log base 2 of n.
We did it! We actually found the value of k. And now that we have that, we can finally state the time complexity of this recurrence. And it's a famous one. It's called O of log n.
So why is k the answer? Well, just think back to our general formula. It was T of n plus k. That k represented the total work done over k steps. So the total time it takes, T of n, is basically just proportional to k, which in big O notation we just write as O of k. And because we just proved that k is equal to log of n, the final complexity is O of log n. And let me just say, this is an incredibly efficient time complexity. But how efficient are we really talking here? Let's put this in perspective. Let's pick a ridiculously huge number for n, say 2 to the power of 64. A linear O of n algorithm would take, well, let's just say you wouldn't be around to see it finish. A really good O of log n algorithm would take 64 steps, pretty fast. But our O of log n algorithm, it would be done in just 6 steps. 6! The difference is absolutely staggering.
So, what's the big lesson here? The takeaway is this. Whenever you see an algorithm that attacks a problem by shrinking it by its square root, you know you're looking at something special. You're dealing with a hyper-efficient solution. It's one of the fastest complexity classes you will ever see. So from now on, when you see a square root in a recurrence, your brain should immediately jump to two things: log n and blazingly fast.